Welcome to the AI seminar. Today we're very fortunate to have Roberto Vega, one of my PhD students. He's done a lot of, he's a dog by the way, he's done a lot of great projects and he's now finished his thesis. His research focuses on how to combine machine learning with medical expert knowledge to learn accurate predictive models. As one example, he's collaborated with a local company, Mito, where he worked with their AI team to automatically analyze ultrasound images for the detection of health problems. Today, a different project related to forecasting COVID in a region. Really cool stuff. I'll let Roberto tell you what he's up to these days. Thank you.
Okay, perfect. Thanks a lot for the introduction, for the invitation. So yes, I'm going to talk about an approach that we call SIMLR. And basically the name stands for machine learning, that is the ML, inside the SIR model. I will explain what an SIR model is in a minute. And we applied this for COVID forecasting. This is a study that we did probably in the middle of the last year. So yeah, let me start by telling you what is like the research objective that we had. So what we wanted to do is we wanted to predict the number of new infected people 1 to 4 weeks in advance. For example, imagine that we are around here in, I don't know, July 28. So we have seen the evolution of the new cases of COVID over this period of time. And then we want to estimate how many people will be infected K weeks from now. And this K can be 1, 2, 3, or 4 weeks. After we make the prediction, then we can check what actually happened. And then we can compare if, or we can evaluate if we did a good job or not a very good job. And the idea is to be as accurate as possible in this sense. So let me tell you basically what is the conclusion of all of this study. So we wanted to apply this algorithm for making the predictions because it is important for taking timely decisions and also for optimal resource allocation. For example, you want to know if you need to put more ventilators on one part or more on the other. And yeah, that is basically the usefulness of these kind of things. So the approach that I am going to present is a combination basically of 3 different elements. One is an epidemiological model, and an epidemiological model is basically a set of equations that people use to predict the evolution of an epidemic, and this is a model from medicine. We combine this with machine learning, and we also introduce a tracking of the policies that have been implemented at the government level. So then we combine these 3 elements to make the predictions, and what we produce at the end is basically something called a probabilistic graphical model. This just means that we can predict not only the estimate of the number of people who will be infected, but also some degree of confidence that, I don't know, it can be like 2,000 people plus minus 2% or something like that. And this approach that we have produced state-of-the-art results in terms of MAPE. This is the mean absolute percentage error. And this is basically a percentage of how much you missed. For example, if you say, I don't know, 80 cases and there were 100, well, the error is 20. 20 over 100 is an error of 20%. So this is how we compute the MAPE. It's just the percentage of error. And we were very successful in doing this. So this is basically the conclusion. We combine these 3 elements and then we can make accurate predictions. Now let me tell you how we do this. So I will start by explaining the SIR model. And again, this is a model used in epidemiology that divides the entire population into 3 different groups. The susceptible, and the susceptible are the people who have never been infected, but can potentially be infected. I mean, the healthy people. Then we have the infected people, who are the people who are carrying the virus at this moment. Then we have the removed people. The removed people are those who already recovered or that unfortunately died. So they cannot transmit the virus anymore. And this is a very, very simple model. And it's assumed that there is no chance of reinfection. Once that you recover, you will never get sick again. That is not true, but it is the model. So when you are in the susceptible group, I mean, if you have never caught the virus, you can either remain as a susceptible person, or you can move to the group of infected. Once that you are infected, you can either remain infected, or you can go to the removed part, hopefully in the recovered people, but we also have some people who die. And once that you are removed, you can now go anywhere else. You will stay in that group forever. That is the assumption of the SIR model. Now, this model is defined by a set of equations that has two parameters. One is beta, that is the transmission rate, and gamma, that is the recovery rate. And well, you go out from the susceptible to the infected by this equation. I mean, the rate of change is just given by minus beta times I times S over SIR. This SIR is the total population, and this model assumes that that is never going to change. There are no new people coming into the community. There are no people going out of the community. It is a static population. So this is how you move. This is the rate from which you move to S to I. And of course, the people who leave S have to go into I. This is where you can see that it has basically the same part of the equation, one with negative sign and the other one with positive. The one who leaves the susceptible go into the infected. And the people who leave the infected go to the removed people by this term, at the rate indicated by this term, gamma times I. And of course, the people who leave the infected are the ones who go to the recovered. So these are the set of differential equations that describe this. And again, this is a model from epidemiology. Now, let me try to give a little bit of insight about the meaning of this equation, or where this equation comes from. Imagine that you have one individual. Then the main assumption of this model, or the rationale behind this equation, is that this person is going to meet beta people. This is why you have the multiplication of this person times beta. Now, what is the chance that any of these beta people is going to be infected? Well, the model assumes that the chance is simply the proportion, for example, of the number of infected over the total population. So this is for one individual, but we have S susceptible individual. So this is where this equation comes from. S is the number of individuals. Each of them interacts with beta people, and the chance that these people are infected is basically the percentage of infected people in the entire population, I over the population. So this is where this equation comes from. Now, what about the people who go out? Well, we have some infected people, and we assume that they are going to recover or die at some rate, for example, every 15 days. So then the number of people who goes out is basically this proportion. Every 15 days, some percentage of the population will either recover or die. And this is where the model comes from. It's a very, very simple model. And there are more refinements of this, but this is the starting point that we took. Now, this is the behavior that can be described by an SIR model. So if you see at the beginning of the time, everyone is susceptible, there is nobody infected, then the number of infected people starts to increase, therefore the number of susceptible starts to decrease, and after a while, the people start to either recover or die. So at the end of time, basically everyone who was susceptible got infected, and all the people who got infected either recovered or died. So there is no possibility to get more infections because that is over. And this is the description of the SIR model. Now, as you can see, this model is actually simple because you can only describe one wave of infections. you cannot describe multiple waves. But we will get to that point a little bit later. So that was the SIR model. And remember, the important parameters are beta and gamma, transmission parameter and recovery parameter. Now, when we work
I have
with...
a question before you go on.
Sure.
The quick question is, keep in mind what questions you'll receive at the end, is that I don't know where on this planet differential equations would be thought of as interpretable to a user making decisions about at-risk populations. Just keep it in mind.
No, that is right. That is correct. But by interpretable, I just meant that there is like an intuition behind this part, right? That we can get like a rationale behind that, but that's it. I agree. I agree. Interpreting a differential equation is
Thank
very,
you.
very hard. Yeah. Now, working with differential equations is hard, mainly in a computer. So what we do is we make a very simple discretization and in this discretization, we basically change the differential equation for an equation of differences, a difference equation. So basically it is the same, just instead of a derivative, we have the difference between two contiguous time points. And yeah, we discretize the data. So from this discrete model, then we can, of course, solve for ST, IT, and RT. So basically, I just transfer these terms from the left to the right, and then we can make inference over this. Note that if we know, for example, the number of people who were infected yesterday, the ST, IT, and RT, the state of the previous day, and if I know the parameters beta and gamma, then we can make inference over the new states, the ST, IT, and RT. And similarly, if I have ST, IT, and RT for today, then we can make the predictions for tomorrow. So if we have this, then we can make the predictions. Sounds easy.
Roberto, a small question.
Yes.
Is T here continuous or discrete valued with you?
Which one?
T, time.
Time. No, time is going to be like a discrete value. And you can decide, for example, if you want to make the predictions at the daily level. For example, T can be day 1, day 2, day 3, or T can be an entire week. Week 1, week 2, week 3. It can be a month. It can be 1 hour. It's up to you, but it is a discrete quantity.
Okay, but the resolution of time will require precision of estimating beta and gamma, right? So
yes.
if you want it hourly, then you have to be very precise in estimation of beta and gamma, so on.
Exactly. Yes. You're right. Now, in terms of the pandemic, we usually do this at the daily basis because this is how the data comes. For example, people tend to report this daily. Oh, we had these new infections and these new recoveries. But you are right. Changing the resolution of this might change the estimation of the values.
Awesome. Great. Thanks.
Mm-hmm. So the next thing that I'm going to do, and this is going to be basically most of the math that I will present, is we can express this set of equations into a matrix form, into matrix multiplication. This is basically just rearranging the terms. Now, the reason why we do this is because we can see that now is linear in the parameters. The set of equations are linear in the parameters beta and gamma with all the nice things that has, like being convex, having a unique minimum. So we can optimize this equation. This is basically the same as the previous slide, just in a matrix form. Now, the important part. How do we find the parameters? Well, if we have a sequence of states, x1, x2, up to xn, and in this case, xt is simply the number of susceptible and the number of infected, then we can build this very simple optimization problem, right? We have, for example, the real number of people who were infected, I don't know, yesterday, that were reported yesterday, the number of susceptible that were reported yesterday, and then we can use our model to make an estimation, x hat, and then we just want the estimation to be as close as possible to the reality. So then it's a very simple optimization problem, the mean squared error. Now, there are cases, and mainly when we have very few instances, for example, when we have only 1 or 2 weeks of data, where this estimation is not going to be very accurate. So if we want, we can incorporate a prior. If some people from the epidemiological side know what are feasible values for beta and gamma, then we can incorporate this, and we can incorporate this as a regularization term, where we are going to penalize deviations from that. This is just a mathematical way of saying, I believe that beta has to be around 1 and gamma has to be around 1/15. And then we can bias the model to try to make the predictions in that. And that is very useful, actually, when we have like very few instances of data. So let me tell you, for example, what happens when you try this equation to fit an SIR model. For example, what I'm going to do is going to be invalid from the machine learning point of view, but it will exemplify a point. Imagine that I collect about, I don't know, 60 weeks of data, and I have the number of reported infections every week over this period. Then by taking this data, I can solve this optimization problem and find what are the optimal beta and gamma that describes this trajectory. Then what I do is something that is called the resubstitution error. Once that I observed the entire data and then found beta and gamma, I will go back, for example, to the week number 17, and I will pretend that I have just seen all of this, and then I will use the parameters beta and gamma to make the prediction of the next part. And it looks like this. It turns out that the prediction is, for example, the orange point, and the reality was the blue point. And then we can do the same basically per every week. And then we have this curve. So how well does it work? Well, the reality is that it is not working very well. Note that we are basically cheating from the machine learning point of view. We saw the entire data, we learned the parameters, and then we use those parameters to make the predictions of the past. And even in that case, we cannot match the curve very well. So it is not working as well as we wanted. Now, what we propose here is to change the parameters weekly. So instead of saying this is the beta and gamma for the epidemic, we can say this is the beta and gamma for this particular week. So then, for example, and we repeated the same experiment. We took the week from, I don't know, the 29th of March to the 4th of April. Then we estimated the optimal parameters. Then we went back to the 28th of March and then used those parameters to make the prediction. And then repeat that for the next week. Again, this is cheating again from the machine learning point of view. But know the difference. For example, if we do this, now we have basically like a perfect prediction. And again, I know that this is not valid from the machine learning point of view, but what we wanted to show with this is that if we allow the parameters to find every week, then we can describe the complex dynamics of the evolution of the COVID-19, even with a simple SIR model. And we cannot do that if we use the traditional version that contains only a fixed value of beta and gamma. Now, of course, the real question is, if I only have data from the beginning of the pandemic until today, then how do I find the beta that will describe the behavior of the next week? That is the machine learning question, because now I'm using only information from the past to try to predict the information from the future. And this is what we do. We started building this graphical model. Well, when this SIR, the number of infected people the next day or tomorrow will depend on the number of susceptible, infected, and recovered people tomorrow, and then we just compare them with today to see the new number of infected. Now, what we can do is we can estimate the parameters beta and gamma for tomorrow as a linear regression of the parameters of this week, the previous week, and 2 weeks ago. So basically, we take the beta and gamma from the past, and then we build a very simple linear regression problem to estimate the parameters beta of the future. Once that we have that, we can make the predictions. So let me tell you exactly how that works. Imagine that we are at this point. We are at August 30. This is the data that we have seen so far. We only have access to the number of recovered, the number of infected, and the number of healthy people. So how do we get the beta and gamma for building this linear regression? We start dividing this daily data into weeks. And then for the first segment, we solve the optimization problem that I showed a few slides ago. And then we find the beta and the gamma that best describe this week. Then we repeat for the next one, and for the next one, and for the next one. And then we take those as the ground truth values, and then we learn a linear regression problem that tries to find like the linear trend in these things. So let's see how it works. Imagine, for example, that we are on the week 16 of the pandemic, and we are going to compare 3 models. The first model is saying, you know what, nothing changes. The number of infected people that you saw yesterday is the same number of people that will be infected today. So then we say that the prediction doesn't change. It is exactly the same thing. The second one is to use the model that I just showed, a model that allows the beta to change every week, and then we estimate the parameters of the week 17 in this case, and then we make the prediction. And then we compare with the ground truth. And the ground truth is this thing. It is coincidence that it worked almost perfectly. It doesn't happen all the time, but it is a nice example. Now, let's look at this particular case. Let's go a few weeks into the future. So now we are at the week 22 of the pandemic, and we repeat the same experiment. So for example, we say, well, let's say that the next week we are going to observe the same number of infections as in this week. So my prediction is that it will not change. Then let's use the model. And just by looking at this trend, we can expect what the model is going to predict. Of course, the numbers are going up. So then the prediction has to be, they have to be following the trend. And in fact, this is what we are predicting. Now let's see the reality. The reality is that the numbers started to go down. Now, at this point, our model has no way of knowing that there is going to be a change of trend. There is nothing that indicates that. You see the data going up, well, then you, of course, predict that the data is going to continue with that trend, but that didn't happen. And, well, when we repeat this experiment for the entire things, we can see an interesting behavior in here. The blue curve is the reported cases. The green curve is something that we call the slow model, because it's the same as the last observed week. So basically repeat your prediction, whatever you saw the last week is the prediction for the next one, and the SIR with multiple parameters. So let's look at this. For example, between the weeks 12 and 20, when we have a very stable trend, then the SIR model makes a very good prediction. It is able to model the trend. Of course, when there is a change of trend, then we make terribly, because then we cannot know that the trend was coming. So then we start to make wrong predictions until the trend becomes stable again, and then we are able to catch up. And the same repeats in here. Now, let's observe the slow model. The slow model is a very conservative model that predicts that nothing changes. So then it has some error all the time, except in the change of trend. Because of course, you are not going to have like you are not going to go from 1,000 to 0 immediately. So basically you start going up, then you plateau, then you start going down. So it turns out that in this transition, saying that the things do not change is actually a very good prediction. So one of the questions is, how do we eliminate these terrible peaks that we have? So if we had a way of identifying when a change of trend is coming, then we can switch to the slow model during that part. So now the question is, how do we identify it? And it turns out that this is where the government policies come into place. And I use this just as an illustration. For example, this is the province of Alberta, and this is data from the from 2020 and the first 3 months of 2021, and this is where we went doing the research. And for example, here we can see the stay-at-home requirement policy that was implemented by the government. So for example, let's look at this increase in the number of cases. The government implemented a stay-at-home requirement at this point. So then we can see that a few weeks later, then the trend started to go down. So it went down, so they say, okay, everything is under control now, so now we can relax the policy. So they relax the policy, and a few weeks later, then the trend started to go up again. And then we can see, I mean, we have had like 4 different waves of this thing, right? And it is correlated with the changes in policy. So now how do we incorporate that in our model? Because when we incorporate that, for example, if we start tracking the things, then we can decide to make the change of policy, and this is basically the SIMLR model. And for example, for the case of Alberta, we can see that it behaves very, very nicely. Why? Well, because there was an important change of policy, it turns out, in this week. So then the model said, you know what, start making conservative predictions here and there, and then we can make appropriate or more accurate predictions. We can eliminate the peak if we can identify that the change of trend is coming. And we do that by tracking the policies. The actual model for tracking the policies is a little bit more complicated, and it has also some problems. For example, we know that, or we believe that if we make a change in policy today, before Omicron, then we were going to see the effect of that change in policy like 2 weeks from the day in which we made the change. Which means that is great, because for example, if I want to make the predictions 2 weeks in advance, I just need to check if there was a change of policy either this week or the last week. What if I want to make predictions in the long term? Well, then I will need to know if the policy is going to change the following week. And that is something that I don't know. So then we have to make an estimation of that. We need to start estimating if we believe that the policy is going to change. So we proposed to incorporate a few notes in here. And we believe that, or this model assumes, that the change of changing the policy the next week or 2 weeks in advance or n weeks in advance depends on basically 2 simple things. The first one is how open is the government to make a change. And then we also make the assumption that this depends on when was the last time that you make a change. For example, if you make a change this week, it is very unlikely that you will be willing to make a second big change the next week. Why? Well, you have to wait at least 2 weeks to see the effect. what if the last change was 2 weeks ago? Well, still, I mean, I have to give it time for the policy to take place, right? What if the last change in policy was 1 month ago? Well, then probably I am very open to the possibility of making a new change. What if it was like 2 months ago? Yeah, sure. If we need to change a policy, let's do it. That is the assumption that we are doing. Now, it not only depends on when was the last time that you applied the policy, it also depends on how urgent is to change the trend. And the intuition behind this node is that it depends on two things. The first one is the number of cases that you have, and the second one is the speed at which they are increasing. So for example, if you have a lot of cases and they are increasing very, very fast, well, then the urgency is big. If there are a few cases, but they are growing fast, maybe the urgency is moderate. And if you have few cases, but it is decreasing, then you say, well, then there is no need to make a stricter policy at this point. So this is what these three nodes in the bottom are doing. And the ones here in the top, they are basically saying, the first node is that the change in trend depends on the changes in policy. If we have seen a change in policy, then we can expect a change in the trend. If not, then we cannot expect that. And based on the change of the trend, we can estimate the new parameters beta and gamma. That is kind of the intuition behind the graphical model. Now, of course, the main problem in here is that we cannot observe the openness to change. We cannot observe the urgency to change the trend. These are like made-up concepts that we did to aid the model. And for example, we basically try to incorporate our intuition as a probability. And this was coming basically from, we call it the domain expert knowledge. And basically, this is just a fancy way of saying, let's use an expert intuition to try to help the model in here. And we can define these tables. For example, if 0 weeks have passed since the last change, then the probability of making a change, that means x equal to 1, is basically 0. And as the time goes by, this probability of making a change, that again is the last column to the right, starts to increase. Where does this number come from? From intuition, basically. This can be thought as a prior, but we use this prior to inform the model when we believe that what are the things that influence the changes. And it turns out that it works surprisingly well. So for example, we make predictions 1, 2, 3, and 4 weeks in advance for the major provinces in in Canada, Alberta, British Columbia, Manitoba, Ontario, Quebec, and Saskatchewan, and in the US as a country. And we compare basically 3 different models. The first one is, or the blue one is SIMLR, the one that we are proposing. The red one is basically the SIR with time-changing parameters, but that do not incorporate the policy tracking. And the orange or yellow one is the slow model, the one that predicts the same as the last week. So we can see that we are quite consistent in the predictions. SIMLR is doing a good job most of the time. Now, that doesn't always happen. There are cases where, for example, in the 3 weeks in advance prediction for Manitoba, we see that the simple SIR model is working a little bit better. Remember that we are incorporating intuition and prior knowledge into the predictions of the model. The quality of the model depends on the quality of the assumptions in this particular case. So if the assumptions are correct, we make great predictions. If they are not, well, the predictions are not as good as we want them to be. So again, there are basically 2 behaviors that we can observe in SIMLR. The first one is when we know that a policy changed recently, for example, we make the prediction 1 week in advance, we can check if we made a change in the policy this week, 2 weeks ago, or 3 weeks ago, and we observe everything. So then the model basically acts like a switch. If there has been no change in policy, then you just use the orange model, right? The SIR model with time-changing parameters. But if you know that a change happened within the last 3 weeks, then switch to the slow model. So basically you select either one or the other. What is the second behavior? For example, when we want to make predictions into the future, then we need to estimate the probability that a change in policy is going to happen. And then what we have is basically a weighted combination of both of them. For example, this is the case for making the predictions on the US 2 or 3 weeks in advance. Look, for example, around the week 15, that the SIR model with time-varying parameters made an over-prediction, and then the slow model made a very conservative prediction. It under-predicted. However, the SIMLR model predicted that there is possibly like a 60% chance of making a change. So therefore, it's going to make a weighted combination of the predictions of the over-prediction, the under-prediction, and it works quite well. I mean, the prediction that it did, it was basically more accurate than any of the two models. Now, so far, we have compared this model against our own baselines. An interesting question that we had is, how well do we perform against the rest of the world? Because there are many research groups that are looking at this same question. So then we made a comparison between our model, the SIMLR model, and the rest of the models that have been submitted to the CDC, the Center for Disease and Control, I guess, in the US. And then we made a comparison between or among all of these models. And it turns out that we do very, very well. I mean, we are not exactly the first place. It is a statistical tie. The variance of both of them is big, mainly trying to make predictions 1 month in advance. 1 month in advance is a lot. But we're very, very competitive. For example, they win on predictions 1 week in advance. We win by a tiny amount in 2 weeks in advance. They win again in 3 and 4. And again, if we make a statistical analysis, we are tied, which are good news. Because, for example, our model, we believe, is a very simple model that can incorporate the domain expert knowledge, and also it can justify its own decision. For example, if it makes the prediction that we are going to see 2,000 new cases the next week, and then you ask, why do you make this prediction? Well, you can backtrack and then you can look at the probabilistic model. And not this one. Sorry. What is it? This one in here. We can look at this. Why do you make the prediction of 2,000? Well, based on the information of the previous 2 weeks, given that we have not seen a change in policy, then we estimate that the values of beta and gamma for the next week are those two. And this is what gives you the prediction. By the way, this is a graphical model, so it will give you also the variance. And what about 3 weeks from now? Well, 3 weeks from now, given the current trend that we are seeing, and given the last time that the government made a change in the policy, we estimate that the probability of changing the policy is 70%. So given that probability, then we estimate that the new parameters of beta and gamma are this, and this is why you get this prediction. with this variance. So that is a nice thing because we can justify the decisions. This model here, this LNQ ensemble one, is actually also very accurate, but there is an ensemble model of 3 convolutional neural networks. 3 neural networks. I don't remember if they were convolutional, recurrent, or what. So they give you a number, but one advantage that we see in our case is that one, we can incorporate the domain expert knowledge to make better predictions, but the second one is that we can justify what we are predicting. One more thing, this model that you see with the dashed line in green, this is the slow model. It turns out that it is extremely hard to make a prediction that beats predicting the same as the last week, even for a prediction 1 month in advance. There are basically only 5 teams that were able to beat this model, at least in that period of time, over 52 weeks that we made. And the rest of the teams were not able to beat that. So it shows how challenging this task is. So what are the conclusions? Basically, we are proposing an SIR model with time-varying parameters, and this model can describe complex dynamics, as the case in COVID. And when we add machine learning, we can estimate the parameters for k weeks in advance, and we can incorporate the policy tracking. And we can also incorporate intuition on the human decisions. And yeah, we create state-of-the-art, we get state-of-the-art results with a simple and interpretable, whatever that means, model. I don't like using the word interpretable because it is subject to interpretation. But well, what I mean by this is that we can get like a rationale, and we can backtrack the steps on the decision, and then we can justify that. The other thing is that this is compatible with many different models. For example, right now, we were using the graphical model to either act as a switch or a combination between the SIR model with time-varying parameters and the slow model. But we can incorporate more models if we want. For example, we have a very big group here at the University of Alberta looking at different things. And some people are basically trying to create a model to estimate what is the behavior under specific changes in policy. For example, they can say, or they are trying to model, well, what if we close the schools? Then what is the effect of that? And what if we remove the requirement of wearing masks? What is the effect of that? What about the vaccination? How does that modify the rate of infections? So if we want, we can incorporate these models into this. So I think that is nice because it is compatible with other models, and I think that they can help each other. Basically, that was like the material that I had prepared. So, and if you want to read the full paper, it's available in that link. So yeah, if you have any questions, I will be glad to take them. Or not.
Great talk, Roberto. It's always nice to see this exciting work going on. So this is sort of founded on the SIR model. And as you point out, there might be other versions and variants of it. Things like SEIR model or having other compartments. Is that easy to fold it into this? You sort of suggest it would be, but any more details about that?
It is. I mean, it is easy in the sense that we can incorporate more nodes in here, and then we can use them to make the predictions. Now, I know, for example, that the SIR model is relatively old, and most of the people are using the SEIR model and variations of that nowadays. The only problem is that I wanted to start with a model where I have all the data that I require. For example, in the SIR, we have the reported number of infections, we have the reported number of recovered, and we have the reported number of deaths. And we know the size of the population of basically all the provinces. That means that we can observe the S, the I, and the R. If we want to incorporate an SEIR model, and the E stands for, oh, I forgot, what is it? SE, is the people who are infected but haven't developed them. Oh, exposed. Exposed, yeah. Yes. So for example, the problem is that we have no observation over the exposed people. And that includes one more level of complexity, because now we need to do inference over that, and then the model gets more complicated. So at this first stage, I wanted to start by choosing something that we can fully observe, and then incorporate the human decisions, and then see if that works. Now that it is working, then the answer is yes. We can start incorporating different compartments, unobserved nodes, and there are techniques for learning with latent variables. In this case, the exposed people.
Okay. That makes sense. Other questions? Something from Randy? That's always surprising.
I already asked my question about interpretability.
Yes. Yes, no, that thing of interpretability is, it is always hard to define or to justify. I use that word just because it is a nice word that
one of the ways to embrace the challenges are to consider who would use these models, because the spectrum of users and the knowledge they have should define how you abstract the predictions that this model will make and how you give them tools. For example, you briefly mentioned adjusting assumptions to be able to see the changes in the prediction based on adjustments in data, for example. That may be more important than the choice of the base model, but it's hard to assess the value until you have a community of users.
I agree. I agree with that. And as you mentioned, the actual user is going to be like the key part that will determine what are the changes that we need to do. For example, if this wants to be adapted and then it wants to be used, I don't know, by the government, for example, well, we can remove most of the uncertainty in trying to estimate what is the decision of the government, because they kind of know what they are going to do. But then they require a different justification than if we want to use this, for example, or if a business owner wants to estimate or wants to use this. Maybe for a business owner, the most important part is going to be like the change in the policy. Are they going to close my restaurant again the next week? Are they going to open it? Because that might determine if I make some investments in there or not, or what do I do with the people who are employed and depend on this, right? So you're right. Depending on who the end user is, it is the requirements of interpretability that they will have.
You will have cracked a major issue if you could ever develop anything that politicians would understand.
Yeah.
Thank you.
No, thank you.
Thanks, Roberto, for a great presentation. Anyone else having questions, please feel free to unmute yourself and ask Roberto directly, or you can type in your questions in the chat box and I'll read those to him.
Yep. Or if you are too shy and want to send an email instead, you can also do it.
Wonderful. If not, I think we'll thank Roberto for presenting his wonderful work today. And we will see you next week.
Perfect.
Well, then, stay safe.
Thanks a lot.
Bye-bye, everyone.
Great talk. Thank you. Bye now.